Okay, good morning everyone. I'm going to briefly go over the lesson on developing the model of the atom, which I would have done today. Obviously, you know today is a snow day, so we are going to go over this. I expect you to please go through this lesson, fill in your notes, and you should have already filled in your atomic theory timeline, so a lot of this is going to be reviewed from what you've already done. Okay, so modern atomic theory, matter is composed of atoms. Atoms cannot be created or destroyed or subdivided in ordinary chemical reactions, okay? When we get into nuclear reactions, they can get subdivided, right? We can split an atom, but we can't do that in a regular chemical reaction, so not like single displacement, double displacement, anything like that. So we know that atoms of different elements have different masses, right? Because they have different number of protons, neutrons, and electrons. And we know atoms are different from one element to another, right? Different properties. So the first theory of the atom is a solid sphere. It's kind of what it looks like. It's Democritus' model. And actually Dalton has the same model. First started looking at this in the 400 BC era. So we're going to go through all of the different main people, which you have already looked at in your chart. So Democritus was the first person, he's a philosopher, that started looking at how matter, or essentially what makes up things, what makes up different types of matter. So really what happened is he started thinking about, let's say you had a piece of a rock, and you split that rock in half, and you take the half and you split it in half again. Eventually, he believed you would get to a point where there would be a limit to how many times you could split that. So his theory is essentially that if you keep splitting any type of matter enough times, you would get to a part where it would now be indivisible. It's like the smallest possible piece. And actually, the term atom comes from atmos, which in Greek means not to be cut. So unfortunately, nobody believed his idea. Okay, they thought he was a crazy person. And the reason why is because they believed another idea from a few philosophers at that time. Actually, Aristotle is the main person who coined this. So they didn't know about elements like how we have elements on the periodic table. They actually believed that everything in the universe was composed of 4 different elements: air, fire, water, and earth. So this is kind of the idea that held true for over 2,000 years, well after Democritus had passed away. So here is our general timeline. So you notice there's a huge gap here. This is where you have essentially them not believing in the idea of atoms until Dalton came along. Okay, so John Dalton, his main theory essentially was to come to the realization that yes, we do have these things called atoms. So here's a summary of his ideas. So matter is made of indivisible particles. Okay, so keep in mind right now we do not know about anything in the atom, no protons, electrons, or neutrons. Atoms of a particular element are identical. And different elements have different types of atoms, and we know that. So there's 2 main laws that Dalton helped to create that still held true today. So one is the law of definite proportions. So essentially what that's talking about is the fact that when atoms combine together to make different molecules, they always combine in a ratio that is constant. So for example, let's take a look at a molecule of water. The ratio of hydrogen to oxygen is always 2 to 1, right? As soon as you change this ratio, you no longer have water. You would have a different type of molecule. And of course, they're always in whole numbers. You're never going to have a 2.5 atoms combining with 3.7 atoms, right? They're always whole numbers, and they are in constant combinations, right? So that's the law of definite proportions. The law of conservation of mass, we talk a lot about that in grade 10. So essentially meaning that whatever you begin a chemical reaction with, you end with the same number of components. They're just rearranged, right? So if I start off with 5 atoms of oxygen, I need to finish my reaction with 5 atoms of oxygen. Nothing can all of a sudden disappear or come out of nowhere. So, sorry, I had to pause that there. So atoms are not created or destroyed. We have to account for everything. So we've already looked at this, right? So Dalton's model, same as Democritus, solid sphere, and there's no other features known at this point. Okay, so Thomson's model of the atom Thomson's main discovery is the electron. Okay, I've posted on D2L a video that will go into more detail how this experiment worked. Essentially, the main idea is that negative and negative repel. So he proved that there had to be something negative inside of the atom because it was repelling this negative plate here. You can kind of see this line going up. So again, please watch that video so you can get a more detailed idea of what happened here. So one big theory or misconception is that Thomson also discovered the proton, and that's actually not true. So what he did do, though, is he believed that there had to be a positive to balance with the negative. So yes, we believe now that the atom is divisible. We have electrons. And he actually hypothesized that the sphere was positively charged and that the little negative electrons are embedded within it. So his model has a bunch of different names. Usually I refer to this as a chocolate chip cookie model. So you have a positive sphere and then the little negative electrons embedded within. So no protons as of yet. Along comes Rutherford. So Rutherford's gold foil experiment, again, so I have a video detailing this experiment. So essentially the main idea here for you to understand this is that this alpha particle, and we're going to talk about this next week, but alpha particles are positively charged. So essentially what he did is he took a thin piece of gold foil, think of aluminum foil but gold, and he shot these almost like little positive bullets, if you want to think of it that way, at the gold foil. And what he noticed is that most of the time, those positive particles went right through. But every once in a while, there would be a deflection. So this picture is nice to see too. So these positive particles, whenever they hit the positive center, they would get deflected because positive and positive repel. Okay, so his main idea here is, yes, Rutherford discovered the proton in the nucleus, and he also discovered the fact that most of the atom is empty space. All right, so let's take a look here for a second. So let's say here is my nucleus, and I have my atom, and I have my little positive bullets. So the fact that these little positive bullets can go right through proved that this entire outside part is empty space, right? But whenever it hit that positive center, right, there would be a deflection because positive and positive repel. So two main things, right? We have the nucleus, which is a positive charge, and the fact that the atom is not a solid sphere. It's actually mostly empty space. All right, so Rutherford's findings, conclusion, nucleus is small in comparison to the whole atom. The nucleus is dense, and the nucleus has a positive charge. Now, we still have electrons, right? So he's still saying, well, hey, you know, Thomson was correct. We do have a negative charge. So he theorized that those electrons are kind of in the empty space around the nucleus. So this is sometimes referred to as the nuclear model. So you have a positive dense sphere, and the electrons are kind of around in that empty space randomly. So we don't know yet about energy levels until Bohr comes along. So Bohr's main contribution is the fact that the electrons are not kind of randomly around. The electrons are in specific energy levels. Okay, so he believed that those energy levels, right, so we can call, they have a bunch of different names, so orbits or electron energy shells. Usually we refer to them as energy levels, but we have different energy levels depending on the number of electrons, and how the electrons move are kind of like planets going around the sun in the solar system, right? So they're kind of traveling around the nucleus. So this leads us to our quantum mechanical model. So this is the modern atomic theory, and actually there are many different scientists that help to contribute to this. But in a nutshell, the main thing that has changed is the way that we think about electron movement. So electrons do not travel around the nucleus like planets going around the sun, but actually they behave more like an energy wave. Or sometimes you can think of it as like bees going around a hive. Okay, so just to give you comparison. So here's our nucleus, and then here we have the first energy level can hold 2 electrons, right? And then after that, the energy levels can hold up to 8, right? So let's imagine we have 3. So this is our Bohr-Rutherford diagram. Okay, now what they've discovered is that electrons don't travel in this way, right? In fact, they actually travel like waves. So that's why sometimes this is also called wave mechanics. So electrons behave like energy. So it's kind of hard to think about, but they're almost like particles that behave like energy instead of behaving like matter. Okay, so it's very unique. So it's kind of a really big discovery about that. So it's impossible to actually know where the electron is going to be. Now, we can make a probable guess, right? So we can calculate where we think the electron is going to be, but not really know 100% of the time. So going back to this, if you want to think of the electron now, instead of being a solar system, like a planet going around the sun, it's more like bees buzzing around a hive. Okay, so imagine my dots are like the electron movement. So instead of staying around in this path, they kind of move around. Now, we can say, okay, this is where the electron might be, but they're not locked in. It's not like a train on a track. They can actually move in and out of this space. And it depends on the amount of energy that they have. The more energy they have, the more space they require. Okay? So going back to this, so sometimes we refer to this as being actually an electron cloud. So instead of having it going around the sun like this, right, going around in a track on a little orbit, we now call them electron clouds because they're kind of moving around in empty space. They're buzzing around. They're not on a train track. So that's why over here, when I do this summary, I'm referring to this as an electron cloud. So this is the modern day quantum model. Okay, so in summary, right, so both Dalton and Democritus believed that the atom could not be divided. The electron was contributed from Thomson, so the electron never went away, right? We still have the electron. And the nucleus was discovered from Rutherford, and the nucleus still exists today. The difference here is Bohr believed the electrons were traveling in an orbit, whereas the wave mechanics or quantum mechanics, they all mean the same thing. Instead of being in an orbit, electrons are now an electron cloud. Now we're going to go into a little bit more detail in the next note, but in grade 12 we talk a lot about this. So in grade 11 we're kind of just introducing you to this idea, but in grade 12 we spend a whole chapter talking about this concept. Okay, so stay tuned for the next video.